parametric equations. Para is just a prefix that means kind of beside, side by side. So parallel means two lines that run beside each other. A paralegal is an assistant for a lawyer beside a lawyer. A paramedic is an assistant to a doctor beside a medic or person. And a metric is just a way to measure or evaluate something. So for example, the metric system is a metric for measuring length, mass, and time. And the ACT is a metric colleges use to evaluate, aka measure, their applicants. Parametric just really means beside for para, and metric, a unit of measure. Beside a unit of measure. Units of measure are commonly called variables. A parametric equation then would just be a relationship between variables beside other variables. When do we see parametric relationships? All the time. For example, we have this fella who's about to throw an orb or a ball or whatever. When he throws it, the ball's position can be seen horizontally or vertically. Both the ball's horizontal position, we can call that our x variable, and its vertical position, we can call that our y variable, can be measured against a third variable, which is time. Let's take a look at what happens when our object begins to fall. So we are measuring our object's horizontal distance and its vertical distance. Our object's horizontal distance can be defined as x of t, so our horizontal distance as a function of time, equals 10 plus 5t. That object's vertical distance can be described as y of t, y, our vertical distance, as a function of t, time, being equal to 50 minus 5t squared. As time increases, our object's horizontal distance is increasing, so our object is getting further from where it was dropped. And our vertical distance is decreasing as time goes on. As time goes on, our object is getting closer and closer to the ground. At time 0, our object's horizontal position is at 10. And I can say that this is meters. And at 3 seconds, our object is 25 meters from where it was first dropped. As time is going on, our horizontal position is increasing. The vertical distance, or the vertical, and I have distance, but I can say position of our object can be defined by this equation. This equation is graphed on this red curve right here. At time 0, the vertical position of our object is 50 meters. At 1 second, so 1 second after our object was thrown or dropped, our object is 45 meters above the ground. After 2 seconds, our object is 30 meters above the ground. And after 3 seconds, our object is 5 meters above the ground. We can see here that we can measure our vertical position against time, and we can measure our horizontal position against time. We looked at this with our graphs, but we could also use these equations. So for instance, at time 0, I can substitute 0 for t. 5 times 0 is 0, plus 10 is 10. So x at time 0 is going to be 10. X at time 1 is going to be 15. X at time 2 is going to be 5 times 2, which is 10, plus 10, which is going to be 20, and so on. I can also see that for this equation down here showing my vertical change, my vertical distance. At time 0, 0 squared is 0 times negative 5 is 0, 50 plus negative 5 is 50, so at time 0 my vertical position is 50 meters. If I substitute 1 for t, so at 1 second, 1 squared is 1 times negative 5 is negative 5, plus 50 is 45. 2 seconds, 2 squared is 4 times negative 5 is negative 20, plus 5 is 50. 3 seconds, substitute 3 for t. 3 squared is 9 times negative 5 is 45, plus 50 is 5. So 50 minus 45 gives me 5. I can also see here that there's clearly a relationship between my horizontal position and my vertical position. just like there was with my horizontal position in time and my vertical position with time. We can define the relationship between the horizontal position and the vertical position, just like we defined the relationship between the horizontal position in time and the vertical position in time. So let's find the equation that defines the relationship between x, our horizontal position, and y, our vertical position. We can do this by eliminating our parameter, which is t. To eliminate the parameter, or to eliminate any variable, we're going to use a system of equations. I'm going to use substitution here to eliminate t. If I can find what t is in terms of x, I can substitute that expression in for t. So let's solve this equation in terms of t. My goal for this side of my equation will be only t, and my goal for this side of my equation will be everything else. First, I'll get rid of this 10 by adding negative 10 to both sides. And then I'll get rid of this 5 that's being multiplied with my t by dividing everything by 5. This will give me t equals x over 5, or 1/5 x, plus negative 10 divided by 5, which is negative 2. T is defined as x over 5 plus negative 2. I can then substitute that expression into my equation in place of t. So I'll kick out this t. And in t's place, I will put the expression that I found that t was equal to, which is negative 2 plus x over 5. Now I'm going to just simplify this equation. I can do that by just following PEMDAS. P in PEMDAS means to look in the parentheses. Here, my parentheses are totally simplified. I can't add those. They're not like terms, so cross it out. Exponents is what I will move on to next. Here I have an exponent of 2, which is right next to this set of parentheses. Exponents indicate repeated multiplication, so I will need to multiply whatever this 2 is next to, which is a set of parentheses, 2 times. 2 sets of negative 2 plus x over 5 multiplied together. I will bring down everything else. Alright, now I'm done with my exponents. Moving on to the multiplication and division step of PEMDAS. Right now, this 50 doesn't have anything that it's going to be multiplied with, so I can just bring it down. Next, I come to 5 times negative 2 plus x over 5 times negative 2 plus x over 5. I have 3 factors all being multiplied together. It doesn't matter the order that I multiply my terms, so I can just multiply the negative 5 with my first factor, negative 2x over 5, and in my next line of work, I can multiply the product of that with my other set of negative 2 plus x over 5. Moving on to addition and subtraction, which is just combining like terms, and I'm all done. This is the equation that defines the relationship between x, my horizontal position, and y, my vertical position. There's that equation once more, and this is the graph for that equation. For our reference, I put our table and our graph of both our vertical distance graphed against time and our horizontal distance graphed against time. Here, time was on our x-axis, and here, our x-axis is our horizontal position, or x. Our y-axis is our vertical position. Instead of having 2 graphs mushed together with time against our horizontal position and also time against our vertical position, we're graphing these 2 parts, our horizontal position against our vertical position. We eliminated our parameter of time. What we'll see is that this relationship is defined by this equation, thus this graph. And I can see that by plotting these points onto this graph.